All right, thank you everyone for coming. Today I'm excited to announce that we have David Wood, who will be talking about hypergraph coloring via Rosenfeld counting.
Thank you, Rose. Thank you for the opportunity to speak today. This is joint work with Ian Wanless, who's my colleague at Monash University, Melbourne in Australia. Let me start with an overview of what I'm going to do. And the background to this talk is very much Lovaas local lemma. This is a powerful probabilistic technique that gets used just all over the place. Every combinatorial mathematician should know about it. But if you don't know about it, that won't affect your understanding of the talk. It's just that it's sort of floating in the background there. So what does it do? It proves the existence of combinatorial objects. It's incredibly useful. A good example of the setting where the local lemma is useful is in the coloring of graphs and coloring of hypergraphs of given maximum degree. And that's what I'll be talking about for most of the talk today. The other background is a very recent paper of Rosenfeld. And the method that's in his paper I call Rosenfeld counting. And so what does Rosenfeld do? He gives a new proof for something that's called non-repetitive coloring of graphs. I'll explain what that is later on. And the previous proofs for this type of graph coloring use the local lemma, or they use something called entropy compression. So what is entropy compression? And again, I'm not going to go into any detail here. This is a method that came out of the Moser-Tardosh algorithmic proof of the Lovaas local lemma. And it's a very powerful method. And people have realized that entropy compression, well, it can prove everything that the local lemma does, because Moser-Tardosh proved the local lemma using this approach. But moreover, if you specialize the method, it can actually give results that are slightly better than what the Lovaas local lemma actually gives. So that's a little bit of background on entropy compression. But this Rosenfeld counting, that's what I'm focusing on in this talk. It's an incredibly simple and very clever counting argument. And it can be used Rosenfeld used it to prove a known bound for non-repetitive coloring. And it has the advantage that it not only proves the existence of a coloring, but it actually proves the existence of exponentially many colorings. And when you read the proof, you realize that the idea in this proof is more applicable than simply for the setting of non-repetitive coloring. And indeed, Rosenfeld states that in his paper, that the method is applicable to other problems, but doesn't go into any real detail there. So what I'd like to do in today's talk, and this is my joint work with Ian Wanless, is to give a single lemma that extends the Rosenfeld method into a general hypergraph coloring setting. And basically, it's exactly the same proof as the Rosenfeld proof for non-repetitive coloring, but it's in a more abstract and more widely applicable setting. It still has the advantage that it gives exponentially many colorings, but now, and it picks up the previous application, but it also picks up a lot of other applications. You can do things like independent transversal star coloring, frugal coloring, Ramsey number lower bounds, KSAT, and other things I imagine as well, using this single lemma that we call Rosenfeld counting. As I said, one of the advantages of this sort of new approach is that it gives exponentially many colorings. Now, many people have pointed out to me that if you push the local lemma a little bit further, or if you use entropy compression and you can push the method a bit further, then they also can prove the existence of exponentially many colorings. What I like about this new counting method is that it inherently and without any extra work implies the existence of exponentially many colorings. And for me, the real advantage is this simple proof. It's this extraordinarily simple proof. It's something that I think you could teach to an undergraduate student, and hopefully they'd even understand it. Okay, so that's roughly where I'm headed today. But first of all, before I jump to the general setting, I want to talk about proper hypergraph coloring. So let me remind you, hopefully, of some basic hypergraph definitions. Hypergraph G consists of a set V of G of vertices and a multiset E of G of edges. So I'm allowing parallel edges in my hypergraphs. Each edge is simply a subset of VG. So it's a very general setting. It's just a set system. Everything's finite, I should say. Coloring of G is a function that assigns one color to each vertex. So coloring for me is very general notion. All I'm doing is coloring each vertex once. There's no requirements on what I call a coloring. But then I say a coloring is proper if no edge is monochromatic. So down in the bottom right here is the Fano plane. You can view it as a matroid, as Rose told me at the start of the talk, which is appropriate given the seminar series. That was unintentional, but it's also a hypergraph. Each line is a edge of size 3, as well as the circle in the middle is another edge of size 3. So this is a hypergraph, and the coloring of the vertices is a proper coloring of the hypergraph. So for example, this edge here has got 2 colors to it, so it's not monochromatic, and every edge gets at least 2 colors. And the chromatic number of a hypergraph chi of G is the minimum number of colors in a proper coloring of G. The degree of a vertex is the number of edges that contain the vertex V. Obviously here the degree of every vertex is 3 in the Fano plane. And also the Fano plane is 3 uniform because every edge has size 3. Hopefully this is something you're familiar with, but I did want to define all these words. Okay, so now let's talk about hypergraph coloring and a very classical theorem of Erdos and Lavas, and who is slightly extended by Spencer. So this is this paper of Erdos and Lavas is the original paper on the local lemma. This is where they invented the local lemma, and their entire motivation was the problem of proper hypergraph coloring. And they proved this bound here, that for every R uniform hypergraph with max degree delta, the chromatic number is at most this expression here. Now the first thing to look at is that the exponent here is 1 by R minus 1. So it's delta to the power 1 over R minus 1, all times some constant that depends on R. So as R increases, the exponent decreases, and colorings get easier as the size of the edges increases. If you color the vertices randomly, then the probability of getting a monochromatic edge goes down as the size of the edges increases. So that's why the exponent there is 1 divided by R minus 1, and that exponent is best possible. I should say that this constant of E here, that's actually not in the original paper of Erdos and Lavas. They proved it with a constant of 4, and then there was a follow-up paper of Spencer who presented the local lemma in a more general way, and that's where the general local lemma is presented. And also Spencer was the one who optimized the constants and got that 4 down to an E, and the E turns out to be best possible for the local lemma. Spencer was also the person, as far as I'm aware, who first pointed out that the local lemma is due to Lavas and not by Erdos. So I think it's the Spencer paper of 77. And from there, everybody calls it the Lavas local lemma. Okay, so what did Ian and I do? Well, we showed this slightly better bound. It's very small improvement, but it is a small improvement. The exponent 1 divided by R minus 1 stays the same. That can't be avoided, but the constant in the front here is slightly better. And as a bonus, you get exponentially many such colorings. Just to illustrate the improvement in the constant, it's best when R is small. For example, when R is 3, the constant in the first result is √3 times E, but in our result, the constant there is 2, which is obviously slightly better. The improvements in the bounds is interesting, but really for me, what is the real value of this this result is this simple proof. And that's what I'm going to show you next, is the proof that for an R uniform hypergraph, the chromatic number is at most this expression up here, which I'll denote by C. Can you see that whole screen? I've got something over it, but can you see that? Yeah.
Yes, we can see it.
You can see that, good. Okay, so this slide, I'm going to go into full details of this proof, not going to omit anything. And this slide is far and away the most important slide of the talk. So the rest of it is I'll wave my hands, and but really, if you're going to get anything out of this talk, this is the slide to focus in on. And all the ideas of this proof, I should say, come entirely from the paper of Rosenfeld. We've just applied it in the hypergraph coloring setting. And the first idea of Rosenfeld is not to just prove the existence of a coloring, but to count the number of colorings. So let's denote by P of G the number of proper C colorings of this hypergraph G. So the number of colorings is C, but we care about the ones that are proper. And now I'm going to introduce a magic number, and I'll call it beta, which is defined to be r minus 2 times delta all to the power 1 over r minus 1. Now, at the moment, you have no idea why I defined beta this way, and you'll see right at the end of the proof why beta is defined this way. It will actually naturally appear. But what we care about is the number of colorings. Okay, so the next good idea of Rosenfeld is the induction hypothesis, and it's a clever idea. And here it is. The induction hypothesis says for every non-empty induced subhypergraph H of G, and for every vertex V of H, the number of colorings of H is at least beta times the number of colorings of H minus V. So you think of it as sort of going from H minus V to H, and the number of colorings when you add a vertex, the number of colorings goes up by this constant beta. But this constant beta is more than 1, or certainly at least 1. So this is telling you that the total number of colorings of the entire graph is exponential in the number of vertices. Because if I apply this induction hypothesis with H equal to G itself, then it says, and then you apply induction, you get that the total number of colorings of P of G, this implies P of G is at least beta to the number of vertices of G, right? So this gives you immediately exponentially many colorings where the base is beta. So you don't directly prove that the number of colorings is exponential. You do the slightly stronger hypothesis that tells you what happens when you just delete one vertex. And that's a really good idea. And once you've got this hypothesis set up, the proof just writes itself. It's really all the cleverness, I think, is in the induction hypothesis. But let's go through this proof. So I've given a subhypergraph H and a vertex V of H, and then I'd say for some edge E incident to V, this notation just means that E is an edge containing V. And I take a C coloring of H, and I say it is E bad if it's proper when I delete V, but monochromatic on E. So I care about the proper colorings of H, but you imagine what can go wrong when you color V is that it might create a monochromatic edge incident to E, incident with V, in which case we say that coloring is E bad for some edge E incident with V. And now probably here's the key observation of the proof. Let's suppose, let's draw a picture. We've got an edge E, and here's a vertex V in here. So there's a bunch of other vertices. Now, I pick one vertex W, which is not V, but it's in the edge E. And I want to care about how many bad colorings are there, E bad colorings. Well, I claim that the number of E-bad colorings is at most this expression here, the number of colorings of H minus E, but not minus W. So let's draw a picture of what this means. This is in blue, the graph H minus E minus W. And I claim the number of E-bad colorings is at most the number of colorings of that blue graph, because you give me any proper coloring of H minus E minus W, and now that vertex W gets one color, and say it's orange, like in the picture, well, that means the only way to extend it to a bad coloring of the entire edge is to color all of the other vertices orange, right? Because the E-bad are the ones that are monochromatic on E. So there's no other option. You have to color all the vertices inside E orange. So we know that the number of bad colorings, E-bad colorings, is at most the number of proper colorings of H minus E minus W. But now we can apply induction at this point. So I apply induction to H minus V. And I get, by the induction hypothesis, that the number of proper colorings of H minus V is at least beta to the power of R minus 2 times the number of proper colorings of H minus E minus W. So where does this beta to the R minus 2 come from? Well, I'm applying induction, and I claim I can apply it R minus 2 times, because to get from H minus V down to what's in the blue graph in the picture, I have to delete these R minus 2 vertices. There they are. There's R minus 2 vertices there. And I apply induction R minus 2 times, deleting those vertices in the green circle, and I get this inequality here. And I know there's R minus 2 there because the edge E has got size R, and so there's R minus 2 vertices, not counting V and W. And now all I have to do is stick all these inequalities together. And here it is. I start with P of H, which is all of the proper colorings of H. And I can write an equality for how many such colorings there are. I take all the proper colorings of H minus V, and then I times that by C, because there's C ways to color the vertex V. But some of those colorings are proper, some of them are not proper. And I care about the proper ones. So I have to subtract away the number of colorings that are bad, meaning they created a monochromatic edge. But that monochromatic edge has to involve V itself. So I subtract away all the E-bad colorings when I sum over all the edges E incident to V. But now I can just bring in my inequalities from above. I care about the number of E-bad colorings. Well, I've just said the number of E-bad colorings is at most the number of proper colorings of P of H minus E minus W. But then you think about this inequality, and it says that this number of PH minus E minus W is less than or equal to, I bring this over here, is at most P of H minus V divided by beta to the R minus 2. So I bring that into here, and the number of terms that I'm summing over is delta, because the degree of V is at most delta, and I get this expression here as a lower bound on P of H. But now the final claim, which finishes the proof, is that this expression is at least beta times P of H minus V. Now, why is that? Well, you imagine all I care about is the C, the delta, so all of that, and this beta. But this inequality within the shaded yellow area comes from exactly the definition of beta and the definition of C. So this is the reason why I defined C this way and I defined beta this way, is so that this very final inequality holds. And subject to that inequality, I just minimize C. I'll talk about how to optimize things later on. And that's really the whole proof. We've now shown the induction hypothesis, and this induction hypothesis applied to the original graph G says that the number of colorings of G is at least beta to the number of vertices of G, which of course is at least 1. So there definitely exists a coloring. In fact, there are exponentially many of them. it's a very clever proof, I think, and all the ideas here I emphasize are straight from the paper of Rosenfeld. You can describe all this proof in terms of probability if you care, if you're more that way inclined, but I think it's quite intuitive and helpful to just think in terms of counting the number of colorings rather than the probability of a coloring being proper. Any questions about this proof? Because this is the key idea of the whole talk.
It's actually not really exactly about the proof, but I was wondering if, so obviously there's a divided by r minus 2 thing here, which is a bit of an issue for graphs.
I'll deal with that in the next slide.
Right.
Yes. Yeah, good point. Yeah, I'm assuming R is at least 3 at this point, but the proof will still work when R equals 2.
It's really nice to see something for graphs.
Yeah, you'll see that. Any other questions? Okay, let's go back. Oh, it's not the next slide. Maybe it's 2 slides time, but I will deal with that. Any other questions on this proof? Because this is the key idea.
Yeah, just one quick question. If it's not like R uniform, can you do like the same thing with taking the maximum of the sizes or something like that?
It'd be the minimum. As long as every edge has got size at least R, then it works.
Okay, thank you.
I mean, if you have a bigger edge, then you can sort of make the edge slightly smaller, and then if it's not monochromatic on the smaller edge, then it's not monochromatic on the bigger edge. Yeah. Okay. So you really can assume, without loss of generality, that it's uniform hypergraph. Okay, so I want to jump to the general framework, and this is how we set it up. This is just some sort of elementary definitions, notation. So let's see if G be all the colorings of a hypergraph G, and for concreteness, let's just assume that that my colorings are integers. That isn't an important assumption. And then I'll also use this notation, C of E, for all colorings of an edge E. Now I'm going to call an instance a pair where G is a hypergraph, and this script B is a set of sets indexed by the edges of the graph. And all it means is that each entry here, BE, is just some subset of CE. I'm not making anything really specific here, but B of E is just a subset of the colorings of E. And you think B of E are the bad colorings. These are the things you want to avoid. And so we say a coloring of the graph is B bad if there exists an edge in the graph such that phi restricted to E is in BE. So it's bad on that edge. And then every other coloring is B good. So a coloring of the graph is B good if on every edge it is good. Hopefully that's an intuitive definition, but there's no restriction on what B of E is. It's just an arbitrary subset of the colorings of E. And now if you think about generalizing the previous proof to this setting, you'll come up with the following definition. You say and a set S, which is a subset of the vertex set of an edge E, determines BE if I take any 2 colorings in BE, and if they agree on S, then they must also agree on, then they must be identical on the edge. So that's a natural notion of when a subset of an edge determines these bad colorings. And this idea was in the previous proof where that vertex W determined the bad colorings for an edge, because the bad in the previous proof were monochromatic colorings. So as soon as you color one vertex, you've forced all the coloring of the other vertices. But this notion now generalizes that idea. And now if you go into our proof, the thing that you care about is, here's the set S that determines everything. You care about the number of vertices that are not in S but are not V as well. And we define the weight to be the number of these green vertices. So that's E minus 1 minus the size of S. So we say that's the weight of the pair VE, and we take S to be the smallest set that is outside of V, and it determines the bad colorings for E. And let's assume for the time being that this is well defined, that it does always exist such a set S. Well, later on in the talk, I'll address the case where there is no such set. And now I care about the number of pairs of given weight. And let's denote that by E sub k of V for the number of pairs VE of weight K. And now this setup is designed so that the previous proof works now in this very much more general setting. And really everything that we did in the previous proof extends to this setting, and we get the following theorem. And I'm not going to reprove it because it truly is identical to what we did previously, but now it's in this sort of abstract setting. We say let GB be an instance and assume there is some real number beta and an integer C, such that for every vertex V of G, C is at least beta plus the sum over all k's of beta to the minus k E sub k of V. So this is this condition. I'm going to call it the key equation later on in the talk. So this equation exactly mimics what was in that previous proof. In the very last line of the proof, you need this equation. But the proof is really exactly the same. You set up an exactly the same induction hypothesis that says for every induced subhypergraph, and so every V in VH, you say P of G, B, C, oh, so that's an H, is at least beta P of H minus V, B, C. Right, it's exactly the same principle as that previous proof, where you define a beta, and whenever you delete a vertex, the number of colorings that are B good goes up by a constant factor, and the constant will be beta. So this is the notation we use for the number of B good C colorings. And so this induction hypothesis immediately implies the theorem that the number of B good colorings of the entire hypergraph is beta to the number of vertices. And of course, this is at least one. So there definitely exists at least one B good coloring. But this is the equation that matters, because this is the equation that enables the induction hypothesis to go through. You'll notice that there's a beta to the K term in here. That's because when you remember, this is the set S that determines the bad colorings of an edge, and the number of vertices that's left over is the weight, and that's the K. And then when you do the induction, you delete each of these K vertices and you get a beta factor at each step. So that's why there's a beta to the K in there. But this proof is really identical to the previous proof, so I'm not going to go through it. But what I want to do now is just give a number of examples of applying this general lemma. First of all, let's check that it works for R uniform hypergraphs, which was the original setting. So you define BE to be the colorings that you want to avoid. So let's define it to be the monochromatic colorings of the edge E. So obviously a coloring is B good if and only if it is proper. And as we did before, every edge of size R is determined by a single vertex W that's outside of V, and you're left with R minus 2 vertices left over. So the weight is R minus 2, and obviously every vertex is in delta edges at most. So this E value of V is at most delta. Here's the key equation, assuming R is at least 3. And you plug in our values for E and you end up with this equation. And this is the equation you need to solve. And you might remember from high school how to optimize such a function. It's a polynomial in beta, this expression on the right, and you want to minimize it. You want to keep the number of colors small. So what do? You take the first derivative of that and set it equal to 0 and solve it, and you will minimize it. So finally, I found something where calculus is useful. And when you do that, you will find that this expression for C is minimized when beta is r minus 2 delta to all to the power 1 over r minus 1, and C is exactly what I said in the beginning. Right, so the process of optimizing this key equation is quite simple. Normally, it's nothing more than take our first derivative and solve it equal to 0. So that's where that expression came from at the start of the talk. And to answer Jim's question, when r equals 2, well, the key equation becomes very simple in the r equals 2 case, because all the weights are 0. And you just get the key equation is that C is equal to delta plus beta. So you just choose beta to be 1. And what does that tell you? It says that the theorem actually gives that the chromatic number is at most delta plus 1 in the case of graphs. Now, of course, that is an absolutely trivial upper bound on the chromatic number of a graph. You just greedily color the vertices and you're never going to use more than delta plus 1 colors. But I think it's a good sign that this general theorem gives you trivial results. And notice that if you change the beta to a 2, then you get a delta plus 2 colors, but then you get a bonus that the number of colors is beta to the number of vertices. So you get exponentially many colors with delta plus 2, beta to the number of vertices colorings with delta plus 2 colors. So you do get exponentially many, which is again an obvious theorem. If you've got 2 choices for each vertex, whenever you color it, you get exponentially many colorings. By the way, just as an aside, the local lemma does not give you this result for graphs. If you apply the local lemma, it tells you that the chromatic number is at most E delta plus 1. So this is not giving you a constant of 1 in front of the delta. Right? So this is an example actually where this method is definitely better than what you get from the local lemma. Okay, let's give some other examples of the generic framework. Something called star coloring. So what's a star coloring? Well, a coloring of a graph is a star coloring if it is proper and every bichromatic subgraph is a star forest. So what does this mean? So I take any 2 color classes and you look at the subgraph induced by those 2 color classes, and the rules of the game says that you must have a star forest between these 2 color classes. So it's acyclic, and in fact it's a forest of stars. And then we denote by chi sub st the minimum number of colors in a star coloring of G. So this is something that people have studied quite a bit. There's at least a handful of papers on this topic. For example, planar graphs have star chromatic number at most 20. That's the best upper bound for planar graphs. But for max degree, Furton, Raspo, Reed first proved big O of delta to the 3/2 upper bound on the star chromatic number for graphs of max degree delta. This was proved using the local lemma. And then sometime later, this result was improved. The constant here wasn't optimized, so I won't say it. But later on, Esperet and Perret optimized the constant using this new method of entropy compression. And they showed an upper bound of √8 times delta to the 3/2. And that's the best known constant in front of this delta to the 3/2 term. But what I want to show is that, in fact, this same bound of √8 delta to the 3/2 just falls out of the general framework in a very natural way. So let's imagine trying to solve the star coloring problem using our generic framework. So we just introduce a hypergraph that models the sort of the bad colorings. So we want the coloring to be proper and we want it to be a star forest. So we just introduce edges into our hypergraph that models those 2 properties. So the first property is obvious. For every edge VW of your graph, you have an edge VW in the hypergraph, and the bad colorings are exactly the colorings phi where V and W get the same color under phi. Right? We want that not to happen, so we put that into our hypergraph. Now, what does it mean to be a star forest? Well, think about a star forest. You can have that 3-vertex path, but you cannot have a 4-vertex path. Now, 4-vertex paths are not allowed to be bichromatic in a star forest, and that characterizes star forests. So we introduce this edge UVWX for each path, UVWX, and those U and W have the same color and V and X have the same color. And so we want to exclude that. So we add that to be the bad colorings for this hyperedge UVWX. So this is not a uniform hypergraph. It's got edges of size 2 and some edges of size 4, but still we can apply the general framework. And all we have to do now is count the weight of these edges. And so the weight of this first edge is obviously weight 0, because here's V and W determines the edge and there's nothing left over. More interestingly, for a 4-vertex path, you pick any vertex V and then you define the opposite side to be S. And now the coloring of S determines the bad coloring of the rest of the 4-vertex path. And so the weight is what's left over, and that's size 1. So the weight of those 4 vertex edges is 1. And now we have to count how many sort of bad edges there are that contain a given vertex. Obviously, each vertex has got at most delta edges of this form, and the number of 4-vertex paths that contain a vertex V in a graph of max degree delta is easily seen to be at most 2 delta times delta minus 1 squared. It's a little exercise. So now we just plug in the generic framework into the key equation, and this is the equation that pops out. And again, you can use high school calculus to optimize this. You take a first derivative, solve it equal to 0, and it will tell you that you should take beta to be root 2 delta times delta minus 1. And then the number of colors pops out to be this expression here, which almost exactly matches the best known upper bound. In fact, it's a tiny improvement. So using this generic framework, you can easily prove results that are known, or in some cases improve the best known results. So always you introduce edges into your hypergraph that model the bad colorings. Okay, my next example is a non-trivial one. This is the setting in which Rosenfeld actually worked, and it's called non-repetitive colorings. So what is this concept? Well, it came out of the combinatorics of words. So we say a path in a graph, this is a path with 2 t vertices, is repetitively colored by phi if phi of vi equals phi of vt plus I for each I and 1 to t. So you think that it's saying that the first half of the path gets the same color sequence as the second half of the path. So if let's use letters for colors, then alpha is a repetitively colored path. And in fact, this edge here is also repetitively colored. But here's a t equals 4 case. And now we define the pi of g to be the minimum number of colors in a coloring such that no path is repetitively colored. So this is called a non-repetitive coloring. So this concept came out of combinatorics of words. The classical result is from 1906 by Toohey, who showed that every path is non-repetitively 3-colored, which is a highly non-trivial result actually. It's not obvious why even a very long path can be non-repetitively colored with any bounded number of colors, but in fact you can do it with 3 colors. And this led Alon, Grichuk, Haluchak, and Riordan to introduce the definition for general graphs. And in the original paper on this topic, they proved a big O of delta squared upper bound on the non-repetitive chromatic number. And the constant in this delta squared term has been slowly improved. The first papers on this all used the local lemma, and then entropy compression came along, and that led to a significant improvement in terms of this constant, of course. The constant got brought down to 1. This is in a paper by Dojmovic, Jouret, Kozak, and myself. And so this delta squared plus big O of delta to the 5/3 upper bound is the best known bound. And it's actually been proved now remarkably in 5 different ways. The original paper used entropy compression. Later, Bernstein introduced something he called the local cut lemma, which also proves this bound. April, in his master's thesis, proved this bound using cluster expansion. Then Rosenfeld proved the same bound using what I'm calling Rosenfeld counting. And that's the method I'm talking about today. And curiously, I recently realized that you can, in fact, get this constant of 1 here using the local lemma. So it's something I call the optimized weighted local lemma. That's another story. But you can, if you push hard enough, get this best known bound using the local lemma. But I want to show that you can get this bound just using the generic framework. And this is how you do it. You define the obvious hypergraph. G prime has an edge E for every path P with an even number of vertices, where the bad colorings for E is just all the repetitive colorings of the path. They're the things you want to avoid. Now, I emphasize that these paths are not of bounded length. They can have any number of vertices in there. They could be all the vertices of the graph. Still, you have to avoid repetitive colorings on Hamiltonian paths. But we can use our framework. We have to think, what's the weight of a path? Well, here's a path, even number of vertices. V is on some side. So you take, to be S, everything on the other half. So that's the S set. And then you observe that a bad coloring of this path is determined by the coloring on S, right? Because that's exactly the property that makes it repetitive. So then you say, well, what's the weight? Well, the weight is exactly everything that's left over. So this one, and this one, and the number of those vertices is T minus 1. So the weight here is T minus 1. Another easy exercise is to show that each vertex is in this many paths of length of 2T vertices in a graph of max degree delta. And now we plug in our generic framework. The key equation holds with this choice of beta and this choice of C. Here I've introduced another variable epsilon because that makes it easier to optimize. And at this point, you would optimize in this equation, and you want to minimize the number of colors. And the way to do that is you take a Taylor series expansion and then just do the first derivative of that and set that equal to 0. You can approximately optimize this to any degree, and this pops out as the right choice for epsilon, and you plug that in, and then you find that the number of colors is delta squared plus big O of delta to the 5/3. It gives exactly the best known bound. And this is what Rosenfeld did, specialized in the setting of non-repetitive coloring. But the generic framework picks up that setting and gives you the same answers. Ramsey number lower bounds. I'm going to say this very briefly because I'm a little short of time. The RCK is your standard Ramsey number. RCK is the minimum n such that every edge C coloring of Kn contains a monochromatic KK. Of course, Ramsey and Erdos and Zekaresh first proved that this function exists. Now, I'm interested in lower bounds here on the Ramsey numbers. So what is a lower bound on the Ramsey number? What does it mean? Well, RCK is greater than n. That means that there is an edge C coloring of Kn with no monochromatic KK. But this is an edge color. This is just a coloring problem. You can model this as a coloring problem on a hypergraph. And our generic framework gives results in this direction. The first results were by Spencer. Well, perhaps not the first one. The first results were actually by Erdos and Zekaresh, where they just took a random coloring. But Spencer noticed that you can use the local lemma to get slightly better. If you just do a random coloring, you get the bound R2K is at least, I can't remember the constant. 2 to the k over 2, I think it is. That's right, but I can't remember this leading constant. Spencer noticed that if you use the local lemma, you get an extra k in here. But you can use our method and you get a slightly better bound. And I don't expect you to try and read these equations. If you think about it long enough and you play with these equations, you will see that these equations are slightly better, only very slightly, but they are a slight improvement over what you get using the local lemma and what Spencer did. But the proof is completely just straight immediate application of the generic framework. You can model this as a hypergraph coloring problem and just apply the key equation and it all comes out. I'm going to skip a little bit of detail here and come to something different. The final example is frugal coloring. What does that mean? You probably haven't heard of that one. A proper coloring of a graph is k frugal if each vertex has at most k neighbors assigned the same color. So here's your vertex V, might have lots of neighbors and maybe it's colored 1. Now it's proper, so none of the other neighbors here get colored 1, but there's a limit on how many neighbors get the same color. So this would be a 2 frugal coloring because the number of neighbors of this vertex that get the same color is only 2. Okay. Now the original result here is by Hein, Malloy, Reed. They showed that if delta is much bigger than k, then there is a coloring that's k frugal. And the important term here is the one on the right. It says the main term is delta to the 1 plus 1 over k, all divided by k, and then times a constant of e cubed. So that's the term that really matters. And in fact, this exponent, this delta to the 1 plus 1 over k divided by k is tight up to the constant factor, which was proved by a lovely example of a LUN based on projective planes. And the point is that this result also can be proved using our generic framework, but let's do it and we'll see something interesting happens here. It's not as simple as you might think, because you model it. First of all, you want the coloring to be proper, so you introduce bad colorings for each edge. That's the obvious one. But now, how do you model the k frugal property? Well, for every vertex V and with k plus 1 neighbors, you have a bad coloring where this vertex, if this was 1 and all these were 2s, that would be bad, because then there would be k plus 1 neighbors with the same color. But what is the weight? Well, obviously these guys have weight 0, but this one, what's the weight here? Well, if these were all the same color, you have no way to predict the color of V. Even if you know that all of those neighbors are the same color, you still can't predict the color of V. So you have no idea. There's no set S that determines the color of this hyperedge. So the weight is undefined. So the general framework doesn't answer this question. But what we did is we came up with a slightly more general framework that does pick up the k frugal setting. So we define in an instance GB a pair VE to be extraverted. I give Ian all the credit for this very colorful language. VE is extraverted if BE is determined by some subset of E minus V. So this is exactly what we had before. We have V and a set S that determines all the colors, and then you define the weight to be the number of leftover vertices. But what if there's no such set S? Well, then we say it's introverted, and we again define the weight of V to be the size of E minus S, but not minus 1, and we allow S to include V. So S would include V. And now it is well defined because there definitely does exist such an S. You can always take S to be the entire edge E, and that does determine the colorings, of course. And now we define weight and we count the number of pairs that contain a given vertex of a given weight. And this is now the new, more general equation. And the proof is really exactly the same as before. The key difference is that you have this C term here, which comes from the fact that that vertex V has got C choices for its color, and you can't really predict them. Now, it might look that this is sort of a circular equation, but it's okay because there is this beta to the minus k term here, and that becomes small, so that you do get solutions to this equation. And you can optimize it in much the same way. Sometimes that takes a little bit more work, but you certainly can do it. Like in the k-frugal setting, you get this theorem by using these extraverted and introverted pairs, because you can model this now using hypergraphs and introverted pairs. These equations, I don't expect you to really see the intuition, but perhaps this corollary tells a story. It says, as delta is big compared to k, the number of k-frugal colorings, where this is the number of colors, C, is at least exponential from the number of vertices, and we've improved the constant from the Hein-Malloy-Reed from E cubed down to E, using just this generic framework, and this is up to a 2E constant of being optimal. I'm wrapping up now. There's further generalizations and applications. You probably know, if you know list colorings, you'll see that everything I've talked about today works for list coloring. There's no harm in having a list of colors at each vertex, and each vertex has to get colored from its own list. It works there. It works for showing K-SAT formulas always satisfiable if the sort of the degree is small. Unfortunately, our results there are don't match the best known bounds. You can get a better bound if you use what's called the lopsided local lemma. And it's actually, I'm not sure if our approach can pick up the lopsided setting. That's something to think about. Independent transversals is another very useful concept. What does this mean? You have a graph and you have a partition of the vertex set, and each part has got lots of vertices compared to the degree of the graph. And then the theorems say that you can always find an independent set with exactly one vertex in each part. That's called an independent transversal. And our methods prove the existence of independent transversals, and the results are slightly better than what you get from the local lemma. Very closely related topic there is constrained colorings. This is list colorings, but you don't specify the size of the list. Here's each edge of your graph. You take the list at V and the list at W, and what you say is that if L of V intersect L of W is small, meaning every pair of adjacent vertices have got few colors in common in their list, you would think there exists a coloring. This idea was originated by Bruce Reed, and he actually made a conjecture that said if this is small, then there is always a coloring. Now, his conjecture turned out to be false, but you still get results in this direction. And this is one example of what we get. It says if you have a list assignment of a graph, and for every vertex V, you sum over all the neighbors, here's the intersection of the lists, and you sort of average it over the neighbors, then our method goes through. And the proof is really the same, except this here is really our beta term, but now beta depends on the vertex. But the idea is exactly the same. You set up the same sort of induction hypothesis and it all goes through. Okay, let me have my last slide. Let me just sort of reflect and compare and contrast on various methods that are applicable for this sort of problem. So Rosenfeld counting is what I've talked about today. I think the big advantage is that it's a very simple and elementary intuitive proof, something you could teach to undergrads. As a bonus, it gives exponentially many colorings. As I said before, local lemma and related topics, if you push them further, can also prove the existence of exponentially many colorings. Rosenfeld counting often gives slightly better bounds than the local lemma. And typically, I think it's fair to say that it's easier to optimize the Rosenfeld counting key equation, certainly compared to the general local lemma, which is a tricky beast to try and optimize. You have to pick these weights in the general local lemma, and it's far from obvious what to do. Entropy compression is this other method that came about out of the algorithmic proof of the local lemma. Often it gives roughly the same bounds as Rosenfeld counting. The big plus of entropy compression is that it gives an explicit algorithm with polynomial expected time complexity. The downside of using entropy compression is that often you need to use non-trivial analytic techniques from enumerative combinatorics to analyze the performance of the algorithm. And this is a plus and a minus. Entropy compression is a method. It's not a single lemma. I like that the local lemma is a single statement of a lemma, and our Rosenfeld counting is a single lemma. But entropy compression is more an approach. So it's not easy to state what is the entropy compression result, but perhaps that has advantages as well because it's a bit more flexible. I certainly know two theorems that have been proved using entropy compression that you can't get straight from the local lemma or from Rosenfeld counting. And they are the Mike Malloy's proof of delta over log delta for triangle free graphs, and also a result of Piotr Micek and co-authors on p-centered colorings. That uses entropy compression plus quite a bit more, and the entropy compression enables you to push it further. Finally, there's more methods in this world of local lemmas type results. Cluster expansion, local cut lemma of Bernstein. I don't know really much about these, but certainly I expect some of these can prove our examples, but the methods are definitely more advanced and certainly less intuitive for at least for me to try and understand. I like the simple elementary counting proof of Rosenfeld. So I'll stop there. Thank you very much for your attention.
Thank you, David. We don't do an applause session at the end, but you can see all the
That's
class
fine,
and chat.
thank you.
Are there any questions for David? So you took at the end something I was going to ask, which was about p-centered colorings. I guess interested that it works for star colorings, but not for p-centered coloring. So do you think that you're just missing a trick to choose the right subset or something like this, or?
No, I don't think it's a small trick is needed. If you look at the paper that uses entropy compression, they don't just do sort of off-the-shelf entropy compression. They have there's a lot more to the proof, let's put it that way. And maybe if you took a lot of more ideas from their proof, you could bring in sort of Rosenfeld counting, but I don't think it would really simplify a lot, because the hard part of that proof is to add on to what you get from end compression. So there's not a lot of advantage in doing that.
Gotcha. Thank you.
Yep.
Question.